My name is Nayana Suvarna, and I'm a Robotics Institute summer scholar from the University of Pittsburgh. This summer, I worked in the Biorobotics lab under Dr. Howie Chose. My project revolves around developing an online decentralized pathfinding framework that can scale to large sets of agents and be applied to realistic robotic systems. Previous work in our lab dealt with a centralized algorithm called MSTAR and its different variants. With this algorithm, a framework called subdimensional expansion is utilized to efficiently plan for large sets of agents. With subdimensional expansion, agents plan assuming they're alone in the world. Then agents' future paths are compared to determine if a collision exists. If a collision is detected between agents, the search space is locally expanded. Then this expanded search space is explored and alternative collision-free paths are calculated for all agents involved. In this diagram, you can see how MSTAR and its variants perform when applied to different sets of agents when planning is uninflated. For our framework, we use a variant of MSTAR called ODrM, which further breaks these collisions down into smaller sets in order to reduce runtime. Although there have been many successful approaches to the multi-agent pathfinding problem, the majority of them fail when applied to real-world deployments. This can come from a variety of factors, but the main culprit is position uncertainties that are caused by imperfect localization and controls. With our framework, we leverage the benefits of online decentralized planning, as well as the scalability of ODrM to address these challenges. The main distinction with our framework is that we are planning in parallel while we are moving. All agents initially plan past their goals, assuming they're alone in the world. When agents get within a specific threshold distance of each other, all agents in range share plans with each other. Upon sharing plans, all involved agents compare their expected paths and determine if an imminent collision exists between any of them. An imminent collision exists when two or more agents occupy the same X and Y position at the same time step. If a collision is present, all agents start replanning using ODrM for the imminent collision set. Whichever agent finishes planning first shares plans with the rest of the agents involved. These agents then stop their individual planning and they proceed on their new paths. Agents then repeat this process until they reach their goals. If no collision is present, agents then can just continue on their paths to their goals and retain information about the expected paths of agents they've interacted with. Through our framework, we distribute the execution of ODrM to run it in real time so that we can replan without needing to delay the movement of agents. To further illustrate this concept, I've included a simple example with two agents above. The filled-in squares represent the actual positions of the agents. The outlined squares represent the goal of each agent. The smaller circles represent the expected paths for agents, and the solid lines represent the actual paths taken. From this diagram, we can see that initially both agents plan their individual paths to their goals. At the next time, we see that the blue agent moves forward and the orange agent rotates in place. Both agents are now within the threshold distance and they share plans with each other. After sharing plans, they realize that an imminent collision exists between them. After replanning, the orange agent now has a new plan that avoids collisions with the blue agent's path. These agents then proceed along their paths until they reach their goals. When testing, we use a simulated environment with Arbus and Gazebo as well as by using ROS. By creating this environment, we were able to facilitate planning while moving, as well as having a testing environment that mirrored a real-world robotics deployment as closely as possible. We used Turtlebot 3 Burger model robots as our simulated agents. In this diagram, you can see 16 agents randomly dispersed in the simulated environment. For our framework, we ran tests of 4 to 16 agents in 2 agent increments. We ran 10 tests per number of agents in an empty 18 meter by 18 meter simulated environment with no static obstacles and randomized starting and goal positions for every agent. While testing, we compared the ratio that exists between offline pre-planning time using ODrM and online execution time. The pre-planning time was the amount of time in simulation that it took for ODrM to compute a plan for all agents in the system. The execution time was the amount of time that it took for all agents to reach their goals with our framework. Through this ratio, we were able to measure the amount of delay in the motion of agents to their goals when ODrM is used. As seen in the graph, there's a general upward trend as the number of agents in the system increases. This indicates that as the number of agents in the system increases, the amount of delay in the motion of agent increases when using offline ODrM. From these tests, we have shown to distribute the execution of ODrM to run in real time on agents without delaying the execution of plans for these smaller sets of agents. Future work on this research would be to apply this framework to larger sets of agents as well as to test maps with different obstacle densities to see how our metric applies. I'd like to thank Guillaume Sartoretti and Dr. Howie Chosit for their support and guidance as they gave me on this project this summer. I'd also like to thank all the RISC sponsors as well as Rachel Burston and John Dolan for making the RISC program possible this year. In addition, I'd like to thank members of the Biorobotics Lab for providing me support as I did research this summer.